Hi, welcome back to this episode on a crash course on Thermo-Calc. This is episode 2, and in this episode we have a case where we're going to look at precipitation hardened stainless steel, because I was pretty curious to know if Thermo-Calc could simulate on kinetics, because that is what happens. We're never reaching equilibrium, but how does it find the intermediate state? Let's take a look in this episode. Enjoy it. First one. Then
Okay.
the next case I have, it's
Okay.
it's a normal known alloy. It's a stainless steel called 74 pH,
Okay.
and the pH means it's precipitation hardened.
Okay. Okay.
So we are playing here with the out of equilibrium content.
Okay.
And typically these steels, they are homogenized, and then they are precipitation hardened. So they're heat treated at a temperature around 500, 600 degrees, where the alloying element that do not like to be in the alloy system, they participate as very small nucleation sites,
Okay.
making the material hard.
Okay.
So I would like to look first into the alloy system.
Okay.
What is the stability of the alloys? So where can we homogenize it? What temperature should we go to homogenize? And then what will happen if we participate harden at 500 degrees? Something like that.
Okay.
So
Great. Okay.
should
Shall we
we?
set up? Do the same
Yes.
again.
Let's
Okay. Yeah.
take a new one.
Okay. So I'll share again. And entire screen. And is it coming?
Yes.
Great. Okay.
It's on.
So again, and I mean, in all fairness, I do have to say that you did warn me of these alloys in advance. So I'm not just. I mean, I did get at least the compositions before this meeting, but still, yeah.
Yeah, you didn't know why.
I didn't know why really, and also I didn't. Yeah, exactly, and also I didn't sort of show you any results. So I hope it's also a bit of a surprise for you to when you see like what comes out if you try these calculations. So so let's try again. True to my principles, I'll start with a single point calculation just to know where we are.
Yeah.
And so tell me.
Yes.
Obviously, iron based again. So I've got
iron based, yeah.
Mm-hmm.
And then we have it's called 17.4. That means 17% chromium.
Okay, easy to guess, yeah.
Yeah, 4 nickel.
Yeah, also easy to guess, right?
Yeah. And then we have the precipitation content, that's copper.
Copper.
So we have 4% copper.
Copper is here. Okay, 4%.
Mm-hmm.
Okay.
Yeah. Then we have 1 manganese and 1 silicon.
1 manganese and 1 silicon. Okay.
Yeah.
And again.
And here I don't have any surprises.
Okay. So I'll do the single point calculation. I'll do it at 900 degrees, actually. Again, I've already looked at this alloy in advance just to see what it actually is. So that's why I choose 900 degrees. And you'll see in a moment why I choose 900 degrees, not 1,000 degrees, right?
Mm-hmm.
He now reads the database again for this new alloy. Okay. And this is the result you get at 900 degrees, right? And what you see again, I mean, again, it's FCC number 1 and FCC A1 number 2. right?
Yeah.
But now, if you look at the composition, FCCA1 number 1 is almost
copper.
pure copper, almost
Mhm.
pure copper. So it's and this is again known, right? There is a miscibility gap between, let's say, the iron-rich side and copper. It's just a miscibility gap. So it's known that if you cool down, you basically get a demixing, if you like, of copper, like in a salad dressing, right? If you have oil and vinegar, you've got little copper droplets that just sort of nucleate out of the FCC. But it's also FCC, right? It's FCC precipitates in an FCC matrix. And I mean, I can quickly go to 1,000 degrees, and then that you'll show that'll show you why I didn't do my normal calculation at 1,000 degrees Celsius. If I do it at 1,000, it disappears. It disappears.
Yeah.
But so something's happening here, okay? And again, I mean, let's just do a one-axis stepping, right, to see what happens, right?
Yeah.
So I go again, one axis, maybe 500 degrees in this case, 1,500 should be enough. I'll move the table and make a plot renderer and perform.
Yeah, because it would be nice to know at what temperature minimum I should be at if I want to homogenize it.
Yes.
That should be possible to see now.
Yes, for sure. Okay, so this is what you get, right? And I mean, there's a lot to say here actually already about this, because the first thing, I mean, you're also a solidification person, right? So the first thing to note is that the primary solidification phase of this steel is actually delta ferrite, which is this red. So I mean, again, if I just increase the scaling here to 1.1, just so it's more clear. The first phase to form is delta ferrite, and then the delta ferrite decomposes to austenite. And then I have a range somewhere between just under 1,200 degrees and just under 1,000 degrees, where it's single phase pure austenite, right? But then, I mean, here already the first question start, right? If I form delta ferrite, will it decompose, right? Because for carbon steels, delta ferrite decomposes very quickly, but for stainless steels, it mightn't. But if you form delta ferrite or not also depends on the cooling rate, right? Because you can undercool the melt and directly solidify it as austenite. So these are all sorts of other interesting questions. But and the next thing to note, that this austenite is not very stable, right? This starts decomposing at rather high temperatures. So I mean, again, I know. Unfortunately, I have not started from zero. I know these steels and I know these sort of curves. So for me, if I look at this, I'd immediately say this is a martensitic steel, right? I would immediately say that this is a martensitic steel, because I would assume that if I cool the austenite here, there is such a high driving force for that to decompose that it will just transform martensitically, right? So I mean, already this curve tells you a lot about this steel, right? And the copper here, FCC number 2 forming.
Exactly. And an extra value, I'm sintering normally.
Okay.
And when you are making a steel like this powder metallurgically, the activity, the sintering activity in delta ferrite is a lot higher than it is in austenite phase.
Okay.
So therefore, an alloy like this, where if I can sinter that at 1,300, where I'm in a pretty large amount of delta ferrite, then I have a higher densification than if there were no delta ferrite.
Okay, interesting. Yeah.
So alloys like the super austenitic steels, 904L types like that has no delta ferrite. If I sinter that at 1,300, I would get a lot lower densification than I do with this alloy.
Okay.
That's also a good sign to have to see how much delta ferrite do I have. Then I know my activity is there.
Interesting. I didn't know that. Okay. Yeah. Okay, so
so typically, what you do with these alloys, they have specific temperatures for precipitation hardening. Uh, One of them is called 482 degrees.
482.
Yeah. I think it comes out of Fahrenheit. I don't know. Is that 700 in Fahrenheit?
Maybe, yeah.
Yeah. So that's why it ended at 482.
Yeah.
So typically what you do, you homogenize it around 1000 is my best guess. Maybe a little higher, 1020, just to ensure that you have the kinetics with you and everything is dissolved. And then you put it in a furnace for 4 hours at
Okay.
482.
Okay. 4 hours. Okay.
And no doubt that this curve shows that the copper will participate.
Yes.
But there are also other recipes where the temperature is higher. You could also do it 650. And
Okay.
why? And are you able in Thermo-Calc to see what will be the difference
Okay.
of
Yeah.
the grain size and so on?
Precipitate size. Okay.
Yep.
So, okay. So this is then moving into a nucleation and growth calculation, right? Because what I do then is I try and set up a nucleation and growth calculation. But before I do that, I have to know out of which phase does the copper precipitate, right? So I have to know what the matrix is. And I mean, just bear with me, because the first thing that this is what I personally would do. The first thing I'd do is I just verify that this steel really has a martensitic transformation, that it really is a martensitic steel. That's the first thing I do.
Yeah.
And we have
I think it's called a ferritic steel. I think you can make it magnetic, but typically it is used as a ferritic. So
okay,
the hardness of it
comes
without
from
the
precipitation.
precipitation, is not very high.
Okay.
When you get the precipitation, it can reach, I think something like 40 Rockwell C, but not a lot.
40 Rockwell and yield strength. Would you know?
Mm, no, I might, but
Okay. Yeah. Okay, but let's just try. I mean, this is so. I mean, I think we've gone for the first. I mean,
mm,
I would like just to mention that if you are interested in seeing if this steel is martensite, we do have martensite models, right? That can calculate if this like on quenching, if this will be martensitic or not. But we can leave that for now, and we can
yeah.
jump straight into the nucleation and growth calculation.
Mm,
Just so that, again, it's a crash course, right? So
yeah.
this is just to show more or less how to set up a nucleation and growth calculation. So we've got the phases, right? 400. It's mostly BCC, right? If we cool this reasonably slowly, that the austenite will probably decompose and it will be a ferritic, so BCC, right? So it's obviously precipitating copper out of BCC. And then, so the first thing that I have to do if I want to do a nucleation and growth calculation, I need a mobility database, because remember the thermodynamic database, that gives the driving force.
Hmm.
Thermodynamics, that gives the driving force. But
Yeah.
I also need a mobility database. So, and I can choose this as a package here, and then he just appends the steel mobility database to the thermodynamic database.
Okay.
Okay. And then I can create new successor and say a precipitation calculator here. And Prisma, and this is what it looks like. And then basically what you have here is you've got the matrix phases, which require mobility data. So not all our phases have mobility data, right? Just the major phases have mobility data. We don't have mobility data for all the minor phases like carbides, nitrides, intermetallic phases. So we just got for the major phases, BCC, for example. And this is the right phase to choose as a matrix, BCC.
Yeah.
Right. And then we've got a whole bunch of things that we can adjust here. If I show the details, and then precipitate phase, right? And in this case, the precipitate phase is simply FCC, right?
Yeah.
And show details again, a lot of things that we can set. And now here again, some words about nucleation and growth, because this is somehow we're starting to simulate something here. And the amount of uncertainties pile up, right? So if you do a thermodynamic calculation, you've got that thermodynamics, it's relatively well established. You can say that's relatively quantitative, right? Then if you move to Dictra, you've got the thermodynamic driving force for diffusion. But on top of that, you've got the mobility and the diffusion models, which have uncertainties. So the thermodynamic database and the mobility database have uncertainties, and the models have uncertainties. So Dictra, you're already starting to have a lot larger uncertainty. And now nucleation and growth, what nucleation and growth does, here you've got even more uncertainties, right? So you've got the uncertainty in the nucleation models. And then how nucleation and growth actually works is it generates new interfacial area that slows down the growth, right? And you've got a thermodynamic driving force that drives the growth. And this interfacial energy, this is another thing that has actually quite a high, we have a model to calculate it, so interfacial energy, but it's just something that's hard to calculate, and there's uncertainty. So we're starting to pile up the uncertainties here.
Yeah.
And but let's see how we get along. One thing I would like to do for these low temperatures is I'd like to increase the mobility of copper, or actually of all elements in the matrix phase, right? And the reason I do this is because, well, first of all, because I've already tried, and it seems required in this case, right? But I mean, there is some logic in this. If you cool this down to low temperatures, it'll be stressed, there'll be dislocations in there, and these things form fast nucleation paths for diffusion. So this is actually something quite standard, that you have to enhance mobility to low temperatures. Also, like grain boundary diffusion becomes more important at low temperatures, and so on. So that's the first thing I'd like to do. And then the second question that we have to answer is, where does that copper actually nucleate, right? What are the nucleation sites? And we can say it's homogeneously nucleated just out of the bulk, which I think is unlikely, but maybe it is, I don't know.
It does. It's all over.
It does. It's all over. What about I would have thought dislocations especially for low temperatures. Well, again, I simply have no idea, right? I simply have no idea. But we can leave bulk, we can do dislocations. Then, of course, if we do dislocations, the question is, what is the dislocation density? Because for high dislocation density, you've got large nucleation sites. I mean, and this is also, if you do these sort of aging treatments, I mean, I know this more from aluminium, for example. Usually you always do it after cold working. So typically you do cold working and then aging. And the reason you do cold working is precisely to have dislocations that'll increase the nucleation site density, and that also increase the mobility. So this is just typical things. But again, let's just try and get a calculation to work. I'll put some nucleation site density here. I mean, again, these are the uncertainties in nucleation and growth calculations. It's not, it depends very much on the process and the material. Okay, and then let's say isothermal. And what did you say temperature? 500 or 482?
Yeah, 482.
482.
If we have to be exact.
Okay. And let's just put 1 day, just, I mean, we can always look
Yeah.
at what happens. And that's basically all there is, right? That's so it's an easy calculation to set up, right? But there are a lot of unknowns here. And I think this is was a bit of my point. And then perform isothermal simulation. And I forgot one uncertainty actually as well. See if he actually calculates something.
As you have seen, we have talked about the mechanical properties of the 17.4 pH steel. And as you can see in the sheet just next to me here, the material without any treatment, that's the one here, has a 0.2 strength on 760 megapascal. But when you make the heat treatment called H900, 900, that is 482 degrees C. By doing that, we have these very fine precipitations that are causing a lot of intermediate blockage for the dislocations, and hence increasing the strength and also increasing the hardness a lot. When you go to higher temperature, 1075, that is 580 degrees C, or if you go even higher, 1150 Fahrenheit, which is 621 degrees C, then you can see that the yield strength is dropping 930 megapascal down to 860. Interesting to see if that can be foreseen as well in the Thermo-Calc simulation program. Nope. Let's get back to Nicholas and his crash course. Yeah, and there was also something about morphology.
Yes, the morphology.
Here
Yes.
it's spheric. It could be needle, but I think spheric is the right one for these precipitations.
Yeah, I would say so too. Yeah, like because it's FCC, right, and it's in a cubic matrix, right? They probably maybe they turn into sort of cuboids, maybe if they get big, but
yeah.
Yeah. And this, by the way, is one reason why we are starting to include elastic constants into our databases, right? Because the morphology of the precipitates, that depends basically on the elastic constants of the of the matrix and also of the that's one of the driving forces for the morphology. So that's one reason why we're starting to look at elasticity. Okay, but he did some calculation, and you actually do get precipitates that start forming. Right now, this is in seconds. So let's have a look at hours. Form length is in micrometers, so let's maybe make that into nanometers. Right. So yeah, I mean, you do get after a few hours, according to this calculation, after a few hours, you do start forming tiny fractions of precipitates. But I do have to say, it doesn't happen so fast, right? And then they grow, and this is then like after 1 day that have reached, let's say, close to 1 nanometer.
Yeah.
And this is so you've got them, right, and they form, right. And now, I mean, again, and this is something I haven't tried this, but theoretically, I could just, if I clone that, I could run the calculation at the higher temperature you mentioned, which was 650.
Yeah.
Right. Just to see what happens. And now the point about again, I've never tried this. I just hope it works, right? the point about the higher temperature is if you go back to the equilibrium calculation, right? So at higher temperature, the fraction of precipitates could be lower. So the driving force for the formation of the precipitates could be lower, but the mobility is certainly faster.
It's a lot higher, yeah.
So the question is, who wins a bit, right? And so I think that would be the like the thing I would like to look at. My feeling is it should grow much better at high temperatures. My feeling. Yeah, I can already see that by the calculation. It takes longer, which usually means they're growing more.
Okay.
Time, it's at a few thousand seconds. So, I mean, the other thing you see, these calculations are also quite fast, right? So they take in the order of magnitude of maximum, let's say, a minute. And what makes them slow is if they're non-isothermal, or if you have complex like heating, cooling cycles, that makes the calculations much slower. But usually, yeah, it'll be under a minute. And he's now.
And in this calculation, you also calculated that nucleation sites were what was that called?
On the dislocations.
Yeah. Not in the bulk, but in dislocations.
That's what I assumed, yeah. But again, this is, and honestly, for these sort of nucleation and growth calculations, as I mentioned, there are a lot of things that have a certain uncertainty. Nucleation sites, but also interfacial energy is something. I'm now just using the calculated value, but that is absolutely unclear if that's a realistic value, right? And especially for these where you've got FCC nucleating and growing in a BCC matrix, one could assume that to start with you have some sort of coherent precipitates, right? Because maybe they're not so different, right? So they might start coherently when they're very small, and then move from coherent to incoherent as the nucleations, as the precipitates grow, and which would mean that you've got a far lower interfacial energy, and and what people do typically is they have certain experiments, right? They did trial runs with similar materials, with similar processes, and then what they do is they try and change all these parameters, like the mobility enhancement factor, like interfacial energy. They try and modify those to fit with their experiments, right? And then they have a certain confidence that for their process and for their material, they're using more or less the right parameters. That's what people usually do. Again, what I'm saying here is that this is, let's say, semi-quantitative method, right? And this is something that has to be calibrated with experiments. So that was about 5 minutes, roughly, which is surprisingly long, actually. And then we can compare the results, right? And actually, one thing, again, this is a crash course in Thermo-Calc, so it's not only about discussing metallurgy, but also handling of Thermo-Calc. So if you want to compare two results, a good way of doing this is we can just click onto one of the plot renders, right-click and say Add Predecessor, and then it makes two arrows going to the same plot, right? And then I can directly compare the two calculations. So precipitation calculation 1. I've got mean radius, and the unit is as, and in the second calculation, I've got mean radius, and I'll put the same unit of as, and perform. And then they should be on top of each other.
Yeah.
And now I just have to know which is which, right? And then probably it would be good to rename this here to rename. You can also rename the calculators to 482 degrees Celsius.
Yeah.
And this one here to rename to 650 degrees Celsius. Okay, and if I click perform again on the calculator, right? Then I've got the two results on top of each other. And yeah, you can see that at 650, definitely it comes sooner, right? And I mean, so that's not okay. It's a logarithmic axis, so let's try doing a linear axis. See what the difference is. Yeah, there's even a bit of a difference in the growth. And now, of course, the question is, right, because you're doing this to improve the yield strength, right?
Yep.
And now, of course, the question is overaging, right? I mean, what happens if you, I mean, again, it's one of these things that calculations can probably just help a certain amount, right? Because you've at the higher temperature, you might also have grain growth. You might have other things that are happening that are not desirable, and you might also have to be careful about overaging, right? So that the precipitates don't grow too big, so that they'll no longer have that strengthening effect, right? So yeah, but basically that's an example of a nucleation or growth calculation, right?
Yeah.
And if I have just a few more minutes, again, just something people maybe are not really aware of, but we do actually also have, we're starting to make a whole bunch of these property models, we call them. And one thing we do have here is a yield strength model. So we could actually also just try with that alloy just to see what our yield strength model approximately, again, what sort of a yield strength we get with that, right? So if I do the yield strength model, so first of all, I have to give it a temperature, because this is a yield strength for precipitation hardened steels, right? So I have to give it a temperature. Let's say the first one was 482 degrees Celsius. And basically that calculates the fraction of precipitates at that temperature. And then we can include things like solid solution strengthening. Let's make advanced here, just so you see all the... Set the matrix phase explicitly. That's important one here, right? Because it's a ferritic steel. So you have to say the matrix phase is BCC. Then we have solid solution strengthening. We can have grain boundary strengthening, which is basically whole pitch, right? The smaller, the stronger, right? So, but here you manually have to set the grain size. So we don't calculate the grain size here. In any way. And the most important one is the precipitation strengthening, precipitation strengthening. And again, we have to set which precipitate is the strengthening precipitate, and it's FCC in this case. We've got a bunch of sort of models that are from literature, but they're specific for a certain group of alloys, like the Seidman model for aluminium-based, Reppich model, or Deschamps model for Reppich model for nickel-based, Deschamps model for aluminium-based. But here it's probably best just to have a simplified model. And then what I can do here is I can just do a one-axis calculation and say mean radius. And so basically just, I could link this to the precipitation calculation, but here I'm just manually saying I've got a mean radius from very small to very big. And I'm just asking him basically to tell me how those precipitates should increase the strength of the material. So, and I won't again, this is something that should be calibrated with experiments, right? So I'm not changing these parameters here, but I'm just using the predefined values, which might be very bad for this material, right? We simply have no idea. But again, what I think the important thing that I'm showing here is that there is at least a framework also, not only to get the size distribution of the precipitates, but also to link that to get the yield strength of this material, right? And we also have a model for martensitic steel strength, right? So if this was quenched, we could also have a look at the what the mechanical properties of this would be if it's a martensitic steel. Okay, and then he's finished his calculation, and just let's see. I hope this gives me at least total yield strength. Yeah, let's have a look.
Yeah.
And that's what you get, right? So you get in function, and again, this is not calibrated, right? So this is absolutely not calibrated, just using standard sort of values. But you get the general sort of, and I'm happy it worked. Actually, I was a bit nervous there. But it's so it's predicting yield strength of roughly 700 megapascal, and then there's this sort of 1 minus 9 maximum, exactly, and then so over here this would be overaging, right? Which means basically, I mean, what's happening here is that if the precipitates are too small, right, then they don't interact with the dislocations, right? That's and then they get bigger, and then so the dislocations have to loop around these precipitates and are very effective at stopping them, right? And then you get a maximum. But once they're too big, the dislocations just go through the precipitates, basically, and you don't have a precipitation hardening effect. That's basically what's happening, and that's what's resulting in this drop down, right? So you get this maximum here.
Isn't it also agglomeration when they grow? They
absolutely.
They agglomerate in fewer particles.
Absolutely. Yes, you're right. Absolutely. So what's this ripening, right? That you have you just have a few big ones, right? And the dislocations have a lot of space on either side just to pass through them. Exactly. So that's the mechanism. So again, I mean, I think that's why I like my job, because I think the what we did today, I mean, this is my day-to-day job. This is actually very typical of what I do every day, right? People asking for like to set up calculations like this and you never know what's coming, right? And it could be steels like these, which are interesting, let's say. It could be anything, right? And this is just that's what we do day to day.
Thank you very much. I learned a lot.
Did you? I'm happy. How was it for you? Like, how was it? I mean, was it instructive or?
Yes, it was very nice. And I remember in my old days, Thermo-Calc was I would say DOS-based. It was very hard to you had to type everything.
Yes.
So this is a lot easier to understand what's going on. Then if we look into the future, Nicholas, there are a lot of talking about developing new alloys using AI. There are these discussion on high entropy alloys or single phase material and multifunctional materials. So how do you think that a program like Thermo-Calc would be one of the tools absolutely necessary to be able to find the new alloy in the haystack?
I mean, what I can say is that high entropy, we have a database for high entropy alloys. We're working quite a lot on that, and it's actually one of our more probably one of our more successful or more important databases, right? And it's trends like these, like a search for high entropy alloys, that is extremely good for us, right? Because this is really where you can to siphon out or to try and focus on. I mean, because the combinations just get so huge. Sure, and I'm sure you've talked about this in previous episodes, right? If you have 10 elements to choose from, and each of those 10 elements, you can go from 0 to, let's say, to a certain amount of percent in 1% steps, you immediately end up with gigantic numbers of alloys. And this is exactly what people do with Thermo-Calc, right? So they do high throughput calculations to according to certain boundary conditions that they want to optimize, to find exactly as you mentioned their needle in the haystack, right? And this can be very different depending on what boundary conditions you set, right? And the boundary conditions can be price, can be corrosion resistance, can be high temperature performance, can be density, can be a lot of things, right? And depending on the boundary conditions you set, you end up with different different alloys, right? And I can tell you another trend that we are basically profiting from a lot is additive manufacturing, right? Because this is again a new process that people don't know about, and they're somehow almost reinventing metallurgy. And so I think these are trends that are, but somehow I'm an old steel guy, right? And I hope that I think people are neglecting steels a bit, and just the old-fashioned alloys that are used in like in 99.9% of the cases, right? And I just hope that not too much resources go on trying to develop something new and forgetting basically how the old things work, right? So
I think the crash course today was in the old.
It was. I'm very happy. Yes, it was very traditional. Yes, it's good.
Yeah, but thank you very much. I
Yes, you're very
enjoyed it.
welcome. Okay.
And if people want to learn more, could they reach out to you? Do you have books or papers or conferences or real courses, not crash courses they should participate in?
Yes, absolutely. I mean, we take part in a lot of conferences, and a lot of sort of metallurgy conferences. You'll see booths of Thermo-Calc. And if anybody's interested, please drop by if you see a booth, drop by, say hello. And I'd say the best go-to place for anybody is just our webpage. We try to put a lot of information and material on our webpage, and it's also a great place, I think, for just finding educational stuff, right? We have a free educational version of Thermo-Calc. You can just go to our homepage. You'll find a button for educational. Download it. It looks exactly like what I presented today. The only limitation is it just says you can just use 3 elements, but you can do a lot with 3 elements, right? You can have iron, chromium, nickel, and do all the stainless steels. You can do iron, carbon, chromium, and do a huge lot of things. You can do precipitation, growth, diffusion. So I really strongly encourage people to just download the educational version. It's fun, right? It's simple. Calculate phase diagrams, just learn about metallurgy, right? Hope people do that.
It should be obligated in every school today.
Should, yeah.
Should. Wonderful. Thank you very much. I really enjoyed it.
Thank you. Great. Thank you, Peter. Thank you very much for having me. Great.
See you.
Bye-bye.
Thank you very much for following this episode. I really enjoyed it. I learned a lot, and I also hope that you learned a lot. One of the things that I hope this episode will give is an understanding on how CalFat can be used. And I really hope that you will share it with your peers if you are working with CalFat or if you are interested in learning more. I think that the opportunity that Nicholas told about, that you can download for free a test program, you can only calculate on 3 alloying elements, but you can learn a lot, and you can learn about the methodology and the nature behind it, the sensitiveness, the parameters that are influencing it. So share it and use it. We need to do this to be better in the future because the world needs us. Thank you.